At noon in Dubai, the same electrical system is being asked to perform two jobs a desert city cannot live without. It must cool millions of enclosed spaces, and it must help turn seawater into drinking water. The year 2025 saw the peak electrical load push past 11 billion watts. The peak daily water demand reached hundreds of millions of gallons. Dubai is building more capacity to meet this surge, but a critical question is beginning to echo through the financial and engineering sectors. Is the city actually expanding its safety margin, or is it simply building a larger machine that can never be allowed to slow down? Because in Dubai, almost every solution to life in the desert demands more from the exact same grid. To understand that immense pressure, you must stop looking at Dubai as just a collection of luxury hotels and tourist attractions. You must start seeing it as one massive interconnected machine. Air conditioning in Dubai is not merely a mechanism for human comfort. Inside the vast majority of its enclosed urban spaces, it is the fundamental condition that allows the city to function. To understand the weight of this obligation, you have to follow the flow of energy. It begins at a distant power plant. It travels through high-voltage transmission lines. It reaches a local substation. It powers massive industrial chillers. It pushes chilled water through endless networks of pipes. And finally, it reaches a glass room. The architectural aesthetic of Dubai relies heavily on glass facades and towering steel structures. But physics dictates that roofs and glass walls act as massive solar collectors. They absorb radiant heat from the relentless desert sun. That thermal energy immediately transfers into the interior spaces. The chillers must then work tirelessly to extract that heat and push it back outside. When the outdoor temperature climbs higher, the thermodynamic resistance increases. The system is forced to consume exponentially more electricity just to maintain the same indoor climate. This creates a profound vulnerability for the entire urban ecosystem. The load on the power grid spikes at the exact moment the entire city is suffering under the most intense heat of the day. Every new square meter of enclosed space built in Dubai is not only a new real estate asset, it is a permanent cooling obligation that will demand energy for decades. When another luxury tower rises along the skyline, we must ask a difficult question. Are we looking at a symbol of economic growth, or are we looking at another permanent relentless load on the electrical grid? But cooling the air is only the first obligation this system carries. The second survival mechanism begins just beyond the coastline. The thermostat on the wall and the water tap in the bathroom look like two completely unrelated utilities, but mechanically and economically, they are drawing their life from the exact same electrical source. And Dubai, drinking water does not come from a natural aquifer or a flowing river. It is manufactured. The journey of a single drop of water tells a story of intense energy consumption. It starts at a massive intake valve in the Arabian Gulf. The seawater undergoes extensive pre-treatment to remove physical impurities. Then it meets the high-pressure pumps. These pumps require massive amounts of electricity to force the seawater through incredibly fine reverse osmosis membranes. The pressure must be immense to overcome the natural osmotic pressure of the salty Gulf water. The salt and dissolved minerals are left behind. The fresh water that emerges must then be treated, stored, and pumped through hundreds of miles of pipelines to reach a kitchen sink. Reverse osmosis relies entirely on the mechanical force generated by electrical pumps. If the electricity stops, the water production stops. The grid is therefore not supporting two separate luxuries. It is supporting the two non-negotiable conditions of urban life in a desert environment. This dual dependency places an extraordinary burden on the utility operators. And by 2026, Dubai is not waiting for this dual demand to slow down. It is actively building faster to keep the system alive. The pressure on the system is accelerating, but we must be careful with our terminology. There is no immediate evidence to suggest the infrastructure is on the verge of imminent failure. Instead, we are witnessing an infrastructure race of unprecedented scale. The peak electrical load in 2025 hit 11.39 gigawatts. The peak water demand touched 487 million imperial gallons per day, and the customer base continues to expand rapidly. In the first quarter of 2026 alone, the city added tens of thousands of new customer accounts in just 12 months. More customers mean more utility meters. More meters mean more air-conditioned rooms, more water pumps, and more illuminated spaces. Each new connection represents a commitment. It must be served not just once upon completion, but every single hour of every single day after it enters the system. The tourism sector is a massive driver of this expansion. New resorts require enormous energy reserves to maintain vast climate-controlled lobbies and expansive swimming pools. But this growth fundamentally alters the equation of urban survival. At what point does continuous growth stop being a pure sign of economic success? When does it transition into becoming a permanent and incredibly expensive engineering obligation? The obvious answer for city planners is to simply build more infrastructure, and that is exactly what Dubai is doing. It is crucial to acknowledge that Dubai is not ignoring this mathematical reality. This is not the behavior of a city asleep at the wheel. Dubai is investing billions of dollars aggressively to remain ahead of the demand curve. The installed power capacity is massive. Recent reports show installed capacity approaching 18,000 megawatts. The city is heavily integrating clean energy. Thousands of megawatts of solar power are already operational at the massive Mohammed bin Rashid Al Maktoum solar park. The desalination capacity exceeds 550 million imperial gallons a day. New state-of-the-art reverse osmosis plants are constantly being commissioned and brought online. The long-term plans stretch to 2030 and beyond, with clear targets to expand both power and water reserves. This sheer volume of investment creates a strong sense of security. It reassures investors and tourists that the city can handle whatever climate or economic challenges come its way. Looking at these raw numbers, it is easy to assume the pressure has been entirely neutralized. But capacity numbers only answer one side of the equation. They tell us how much the system can currently supply. They do not answer the much more dangerous question of how much the city will eventually demand. Adding new capacity does not end the cycle of dependency. In a rapidly expanding economy, adding capacity actually makes the next round of urban expansion possible. This is what systems engineers refer to as the Red Queen race. It is a concept taken from literature where you must run as fast as you can just to stay in the same place. Dubai is constantly moving forward and building larger power plants, but a massive portion of that new development is required simply to stop the rising demand from closing the distance and eating away the safety margin. When a new substation is built, it allows for a new neighborhood to be developed. That new neighborhood brings more residents, more retail spaces, and more cooling requirements. Those new requirements immediately consume the buffer that the new substation was meant to provide. To me, this is the most fascinating and revealing part of the underlying economic story. Dubai's engineering is not failing. It is succeeding so completely and so effectively that ordinary life can no longer be imagined without it. The city has successfully isolated its economy from its geography. But is that true resilience? Or is it simply a much deeper and more expensive form of dependence? Dubai is not trapped because it cannot build enough power plants. It is trapped because it can never declare the infrastructure job officially finished. And that profound dependency looks very different when we stop measuring it in gigawatts and step inside the actual economy. We must move away from the macroeconomic data and look at the physical spaces where this energy is consumed. Consider the interior of a flagship luxury hotel. The environment inside is a masterpiece of artificial climate engineering. The central air conditioning runs flawlessly. The ventilation systems constantly filter and cycle fresh air. Elevators move thousands of people vertically every hour. High-pressure pumps ensure hot water reaches the 50th floor instantly. The commercial laundry facilities process tons of linens daily, requiring massive amounts of heated water and electricity. The entire tourism experience depends strictly on this unbroken chain of temperature stability. But this brings us to a hidden vulnerability connected to the wider tourism economy. What happens when global travel trends shift? If regional instability or a global economic downturn causes a drop in visitor numbers, the hotels face a severe financial paradox. A hotel operating at 50% occupancy still needs to cool its grand lobby. It still needs to pump water to its upper floors. The building still absorbs the exact same amount of solar radiation from the desert sun. The energy demand of the building does not drop perfectly in half when the guest count drops in half. The enclosed spaces still demand their climate. Inside a sealed tower, which mechanical system is truly optional. You cannot turn off the ventilation without rendering the building uninhabitable. You cannot stop the water pumps. The cooling system is what makes every other square foot of the property usable. This means the energy cost acts as an inflexible floor for the tourism industry. When revenue fluctuates, the energy obligation remains rigid. Now take that single vulnerable building and place it alongside every other structure under the exact same summer afternoon. To truly grasp the scale of the challenge, we must conduct a hypothetical system stress test. This is not a prediction of an imminent blackout. It is an exercise in understanding how systemic loads compound upon each other. Step 1 begins as the sun rises higher in the sky. The ambient air temperature climbs rapidly. The glass towers begin to heat up, forcing the building management systems to command more cooling. Step 2 activates the heavy machinery. The industrial chillers ramp up their compressors. Massive fans spin faster to reject the heat into the already sweltering outdoor air. The district cooling plants, which supply chilled water to entire neighborhoods, pull enormous amounts of power from the grid. Step 3 involves the invisible flow of water. As millions of residents and tourists wake up and begin their day, the demand for fresh water spikes. The reverse osmosis plants must maintain high pressure. The distribution pumps must work harder to keep the reservoirs full, while simultaneous consumption drains them. Step 4 introduces the burden of the grid operator. The utility company cannot merely supply the exact amount of electricity being used, they must maintain a spinning reserve. They must prepare for the possibility that a transmission line might trip, or a generator might need unexpected maintenance. They must balance the influx of renewable solar energy, which can fluctuate with passing clouds, against the rigid, unyielding demand for air conditioning. Step 5 is the real-time balancing act. Electricity must be produced and consumed at almost the exact same millisecond. Battery storage is improving, but it cannot yet run a sprawling metropolis for days on end. Every single element, from the power plant to the hotel thermostat, must execute its role perfectly. Nothing has failed in this scenario. But every additional load, every new tourist, every new air conditioning unit consumes a little more of the breathing room that operators must preserve for the unexpected. And that reveals the real risk hiding beneath the surface. It is a risk much quieter than a sudden blackout, but far more permanent to the economy. The ultimate pressure on Dubai is not that it will suddenly run out of electricity. The pressure lies in the continuously growing amount of infrastructure capital investment and technical complexity required just to keep a safe distance ahead of the demand curve. When you read that the city has almost 18,000 megawatts of installed capacity, you cannot simply subtract the peak load of 11 gigawatts and assume the rest is pure, uncompromised backup. Operating a grid is immensely more complex than simple subtraction. Installed capacity does not mean all capacity is available at every second. Power plants require scheduled downtime for critical maintenance. Transmission networks have thermal limits on how much power they can carry during extreme heat. The integration of solar power means that a portion of that capacity disappears when the sun goes down exactly when evening cooling and lighting demands begin to rise. The margin of safety is an operational reality, not just a number on a balance sheet. The electrical grid is not simply supplying a city with power for televisions and laptops. It is actively helping to manufacture the fundamental environmental conditions that allow the city to physically exist. Electricity in Dubai is no longer just a basic public utility. It has become a structural component of the urban climate itself. The grid does not only power the future ambitions of Dubai, it acts as a permanent shield that protects everything Dubai has already built in the past. If that shield becomes too expensive to maintain, the entire economic model faces a profound reckoning. Dubai is highly aware of this paradigm, and engineers are deploying sophisticated solutions. But when analyzing these solutions, we must ask a critical question. Does a solution actually reduce the total demand of the city, or does it only reduce the energy required for each individual unit of demand? Take district cooling as the prime example. District cooling plants generate chilled water centrally and distribute it to multiple buildings. It is vastly more energy efficient than having individual air conditioning units on every building. The city is heavily pushing to expand district cooling networks. But the conflict is that saving energy on each square meter of cooling does not guarantee that the total energy demand will drop. If the city builds 10 million new square meters of real estate, the absolute demand still rises, even if it rises slower than before. The same paradox applies to reverse osmosis desalination. It is incredibly more energy efficient than the older thermal desalination methods that boiled seawater. But the transition to reverse osmosis binds the production of water directly to the electrical grid, creating a tighter dependency. Solar power and grid storage add crucial layers of clean energy. Solar generation perfectly matches the midday cooling demand profile, but it still requires vast transmission networks, flexible backup generation, and highly advanced demand-side management. Upgrading building codes and retrofitting older structures to be more energy efficient are vital steps. The city aims to cut its baseline energy and water usage significantly by 2030. Efficiency is the only way to widen the safety margin, but if continuous urban and tourism growth consumes every single megawatt saved, then efficiency simply becomes a way to continue running the race. It is not a way to finally leave the racetrack. This brings us to the core economic reality of building a metropolis in the desert. It is a concept we can call the energy debt. This is not a traditional financial loan issued by a bank. It is a permanent environmental and operational obligation created the moment a new project breaks ground. A spectacular new hotel can be funded, constructed, and opened within 3 to 5 years, but the energy debt of that building will last for 50 years. The grand interior spaces must be cooled every single day. The water must be continuously pushed through the desalination membranes to fill the pools and serve the guest rooms. The substations feeding the property must be relentlessly maintained. Older power generation equipment will eventually degrade and must be replaced at great cost. The utility grid must forever remain one step ahead of the building's needs. The real cost of a breathtaking skyline is not paid in full when the concrete finally dries. It is paid again every single summer. It is paid every afternoon when the sun hits the glass. It is paid each time the mechanical system must fight physics to keep the interior climate cooler than the hostile world outside. If tourism metrics fall short of projections, the revenue to pay this debt weakens, but the debt itself does not disappear. The more successful Dubai becomes at separating its luxurious urban life from the harsh realities of the desert environment, the more resources it must spend to ensure that separation never fails. Which brings us back to the two objects that looked so completely ordinary at the beginning of our analysis. The glass of fresh water resting on the table, the thermostat glowing on the wall. They are not just amenities, they are the end result of a staggering logistical and physical battle against nature. Dubai has not failed to overcome the desert. It has succeeded by building an extraordinary and unimaginably complex machine that negotiates with the desert every hour of every day. The fundamental question for the future of the city is not whether that massive machine works today. It clearly does. The question is how much larger and more expensive that machine must become tomorrow. How much more capital must be spent just to keep the water flowing, just to keep the towering glass structures cool, and just to keep everything feeling exactly the same. This documentary examines documented infrastructure growth, energy demand, and economic patterns in Dubai. It relies on public data regarding electricity cooling and desalinated water systems. This analysis does not predict an imminent blackout or a failure of the water system. Any hypothetical peak demand sequence detailed in this video is an analytical stress test. It is designed strictly to explain infrastructure dependency and economic vulnerabilities. It is not a forecast of a specific catastrophic event. Economic and tourism conditions are subject to change. Do you see this continuous infrastructure expansion as a testament to human resilience? Or do you see it as a deeper and more vulnerable form of dependency? Tell us in the comments where you think the line should be drawn between sustainable growth and permanent energy debt. If you value documentaries that look deeply beyond the polished skyline and investigate the hidden systems that run our world, make sure to subscribe. The next warning sign is rarely exactly where the tourist brochure tells you to look.